Thank you for the introduction. I am Mahmoud from FMT Group, Poland University. In fact, our group is interested in additive manufacturing, laser welding.
I should go on the stage.
Okay. Our group is interested in the additive manufacturing and whether by laser powder bed fusion or WAM, even for the polymers, as well as we perform laser welding. I joined the group 2 years ago. Now I'm a postdoc. Therefore, I performed some analysis at the University of Ouro to some works that I did in Egypt, where I am originated. In addition to, I will present today some laser welding and TIG welding of additively manufactured 316L stainless steel. So this is the outline. The first topic is about the gas tungsten arc welding of low carbon steel with nickel chrome and medium manganese steel. The second topic about the influence of GITAO and SMAO techniques for weldability of low carbon manganese steel. And the third one about the indentation behavior of actively manufactured 316 stainless steel, whether by laser or TIG techniques. The first topic, we will talk about the medium manganese stainless steel welding with nickel chrome stainless steel and low carbon steel. Background about this topic, that the 300 series stainless steel is widely used, but for some economic regards, then there are some direction to the replacement of this stainless steel with the 200 series. As for economic regards, therefore, nickel chrome stainless steel, which is a type of 300 series stainless steel, will be replaced with medium manganese stainless steel, which is 200 series stainless steel. Then we will explore the weldability of the medium manganese stainless steel with low carbon steel and nickel chrome stainless steel. The welding was performed at different heat temperatures. Here is the chemical composition of the investigated material. Regarding the nickel chrome stainless steel, it has like 18% chromium and 7.8 nickel. For the medium manganese stainless steel, chromium and nickel were reduced, while manganese was increased to keep more region for austenite. The methodology, we use GITAO technique. The dimension of the plates were 200 meter times 100 meter, and the thickness was 2 millimeter. Joint type was butt joint, and the shielding gas was pure argon. Then we get some specimen for microstructure, hardness, and specimen for tension tests. Furthermore, we use two different filler method. The filler method with molybdenum was used for the welding for the low carbon steel with the manganese steel in order to give some chance for carbide precipitates at fusion zone. And then we can increase the joint efficiency. The heat input was calculated by this equation. Then we have the current, voltage, and speed of welding and efficiency of the process. These are the heat inputs which we investigated in this study. For the result and discussion, the low carbon steel has BCC structure, ferrite and perlite, and for the nickel chrome and medium manganese steel, they have fully austenitic structure. This by optical and EVC. And regarding inside properties of the material, the low carbon steel here is represented by the blue line, and the medium manganese steel give higher strength but lower ductility than the 300 series. Then after welding, we start with the radiographic test to ensure that the welding has good properties. We found that some porousness were formed at the edges of the welding joint, therefore it was neglected, and the specimens for tension test and hardness were selected from center. Regarding the medium manganese stainless steel site, we found that there was a transition zone between the base metal and the fusion zone, and this transition zone happens due to sensitization at where the chromium and carbon can be depleted from the grain to form some carbides at the grain boundaries. Yes, and this transition zone also was noticed in the nickel chrome stainless steel site. For the low carbon steel, only there was grain coarsening in the heat affected zone. The main study here was regarding the amount of delta ferrite at different heat inputs, and we found that with heat input here, the heat input in red is the higher one, and in black is the lower one. Then with the heat input increase, the amount of delta ferrite was increased. We calculate the delta ferrite by using ferrite scope. And for this reason, we know that when we give the material more high heat input, then the fusion pool will be increased, and then the cooling time for the fusion pool will be decreased. Therefore, at higher heat inputs, the amount of delta ferrite will be decreased, because some of this delta ferrite will be transformed into austenite. And regarding the hardness results, we found that here in the low carbon steel side at the fusion zone, that with heat input increase, the hardness was increased. However, there in the medium manganese steel with nickel chrome stainless steel, with the heat input increase, there was some reduction in hardness, and this reduction in hardness due to formation of wider arms of the dendritic structure of austenite and ferrite dual phase in the fusion zone. Here is the tensile properties of the welded joints. We find that with the heat input increase for the low carbon stainless steel, the joint efficiency was increased. However, in that stainless steel joints, there was a reduction in the strength with the heat input increase. And here is the fracture location. In the low carbon stainless steel welded joints, fracture happened at the site of the low carbon steel. However, here in the the stainless steel joints, the fracture happened at the weld zone, means that the weld zone was having lower strength than the base metals. And the fracture surface, there was no big difference between the fracture. Most of the specimen gave ductile fracture. And this was the conclusion for this study, that the fusion zone showed topic structure of snide and delta fry. Delta fry content was decreased with the increase of heat input, while the width of the fusion zone and heat affected zone was increased with the increase of heat input, and hardness value increased with increase of heat input of low carbon steel. However, hardness decreased with the increase of heat input for the stainless steel joints, and the dendritic feature were promoted in all fractured joints. Yes, that's all. For more information about this study, that was published the last year. Yes, thank you.